Hello, everyone. We now have working mic. All right, so this is probably going to be a little bit of information, but I'm just going to walk you through it. So we're talking observational studies versus experiments. How do we use experiments, observations to explain causation? This first part we went over in class, but I'll just go over it again so that you have it to review. So an observational study observes individuals and measures variables of interest but does not intend to influence the responses. So you are not doing any treatments at all. You're just observing what has happened. You're making observations, inferences, okay? An experiment deliberately imposes some treatment on the individuals to measure their response. So you are doing something to the experimental units, to the subjects. You're actually changing things. Confounding occurs when two variables are associated in such a way that their effects on the response variable cannot be distinguished from each other. So anytime you're observing, you don't know which variables are affecting the outcome, the response. And so there are multiple explanatory variables, and so it's confounding. A lurking variable is a variable that you might not be aware of that you're measuring. So as you are looking at different things, you're not quite aware of its presence until retrospectively maybe, or something happens that makes you realize that there's something else that's connected. And so you're not actually measuring that variable at the time, but it's what is actually causing there to be a correlation or a relationship between the two variables. That's why you see an association. But observational studies of the effect of an explanatory variable on a response variable often fail because of confounding, because of lurking variables between the explanatory variable and one or more other variables, all right? So any specific condition applied to the individuals in an experiment is called a treatment. So we always want to identify how many treatments, and like we were looking at today, based on the number of treatments that you have, then you might have one more treatment for the control, and we'll get to that later. But if an experiment has several explanatory variables, a treatment is a combination of specific values of these variables. So you could have lots of different treatments and not just limit yourself. Experimental units are what we are applying the treatments to, and we call them subjects when they're human beings. The big advantage of experiments over observational studies is experiments can give good evidence. We have reason to believe that this, when we did this, it caused this, especially when we have a control group in there, because you have something to compare it to, and so we like comparative studies. Sometimes we call explanatory variables factors, and when you combine a certain factors in a certain way, we'll call those different things levels when you're studying that joint effect of several factors. We always like comparative so that we can get rid of the confounding. So we're trying to eliminate all the other variables that could naturally change as a result of different things by using random assignments, by having control groups. So experiments do a nice job of getting rid of all these extra variables that we have in place by allowing them to become statistically insignificant. So we've got to make sure that our groups aren't biased, though, and we use random assignment for that. So chance process helps ensure that our other random variables are spread evenly throughout the groups or randomly throughout the groups. We don't want to, if we try to think through, well, I don't want it to be a guy versus girl, or like when we were talking about the caffeine intake and talking about athletic versus non-athletic, you don't want to split up those things equally because you're automatically going to mess up a different variable, a lurking variable potentially that you didn't think of. And so when you try to eliminate variables on purpose by picking and choosing, you can create more issues for yourself without realizing it, which is why we just use random assignment, because then randomly everything will kind of fall into place if we have a large enough sample. So we have our CR, so comparison. So we want to compare the different treatments. Random assignment to eliminate bias. control to eliminate other variables that might affect, and replication so that each group is getting that same treatment and that we could redo this and it's not like a chance that all this happened. Okay, completely randomized design. This is what we started doing the little mapping today. So you have your experimental units, and that goes into a random assignment, group 1, group 2. It could be group 1, group 2, to group 3. Each group is going to receive a different treatment, and then we come back together and we compare the results. So control groups provide a baseline so that we can measure the effectiveness, because we want to be like, well, was it the weather? Was it what they ate? Whatever it is that could have changed over the course of the experiment, well, this helps us see. Okay, so this is, you could have a double blind, so that's what we were talking about today with neither the subjects nor the people interacting with the subjects know which treatment is being given to the subjects. You can also have single blind, so either the people receiving the treatment or the people interacting with the treatment, one of those two groups doesn't know which treatments are being given, so that we don't create bias, like how when we were talking about the order of the questions asked in our surveys can sometimes create bias. By eliminating people knowing, then they can't cause an effect on it, okay? So we want to be able to see an effect so large that it's considered this, no way this could have happened by chance, so that would be statistically significant. And as we get into future chapters, we're going to be looking at, well, what constitutes statistically significant. Right now, we're just going to be like, well, that could not have happened by chance. It's obvious that there was a general increase, or whatever it is, and that's how we're going to measure it for now until we get into specifics in the future. So think of a block design like a stratified random survey. So that is where you're going to kind of group people into blocks before, or experimental units into blocks, because you know that they're similar in some sort of way. You can do a randomized block design so that each of the units is carried out separately within each block. So you could do this with separating men and women to see how it affects each one. Like they just decided, I saw in the news, that 99% of all breast cancer affects women, but 1% affects men, and so they just decided that we have to start measuring the effects of drugs and treatment plans on men as well as women for breast cancer. And so this might be where a block design would come in, is you would look and see how that would affect men versus women. When blocks are formed wisely, it's easier to find convincing evidence that one treatment is more effective than the other. We control what we can, block what you can't control, and randomize to create comparable groups. So try to do what you can, because you don't want, like, if you were to just throw in the random man into each of your different treatments, then we wouldn't be able to measure the effects well. And so you can't control the fact that only 1% of the population of breast cancer patients are men, so that's why you might block it, because you can't control that. Now, a matched pair design is kind of what Yasmin was referring to today, but so you would give either, you would set up similar pairs, so like a husband and wife, so that they're same factors that they are experiencing at home, and you'd give the husband one treatment and the wife the other treatment, and you'd randomize which husband and wife that would get each treatment. Or you can have it like how we were talking about a matched pair design, where it's a single subject or a single experimental unit is going to receive both treatments. And so you still have to randomize over and over again. Just get used to randomizing everything, because we don't want anything to be our choice at the end of the day, because if it comes down to our choice, our brain naturally tries to make sense of things and create patterns, or tries to avoid patterns and then creates patterns. And so we do things by using these random number generators or random tables so that we can eliminate any of our personal bias. So hopefully this is helpful. I'm also just going to post these notes without my commentary so that you can do it either way. Hope you all have a great evening, and we will see you tomorrow.